So today we're going to be looking at different graphs of functions. We're going to be finding domain and range. I'm losing my voice, sorry. Using the vertical line test, determining what intervals of a graph are increasing or decreasing, finding the relative max and min, and looking at piecewise functions in addition to determining if a function is even or odd. So we have a lot of stuff going on. So we're going to start with example 1. So I'm going to make it bigger so that you can see what's going on. And so for example 1, we're to find the domain and range just by looking at a graph. So we're looking at this graph right here, and notice that the graph starts here, goes through this point, and ends here at this ordered pair, and this is an open circle. This is a closed circle. So the only hole in the graph is all the way here. This means that this ordered pair, which is at 4, 0, is not a solution to the graph, but any ordered pair that comes close to 4, 0 but isn't 4, 0 and doesn't go past 4, 0 is is a solution to the graph. So how do we find, or how did they find this domain and range? If I were you, I would take a highlighter. And for domain, we want to see where the graph touches the x-axis. And so I'm going to take this and bring it up to here, and oftentimes I'll just do a full highlight of the line, the vertical line at which it touches, and a full highlight here. So that's the start and the end of the graph. So there's no graph over here to the left, and there's no graph over here to the right. The graph is going in between these two poles, if you will. And because this endpoint is closed and this endpoint is open, that means that it's going to start and include this value here, and it's going to go and end here, but not include this value here. So this x value here is -2. So I'm going to put a -2 right here, and this this x value here is a 4. So that's how they got, and that's how they went from the -2. We start at -2 and we go to 4. That's how they got the 4. Now the brackets and the parentheses. So you might want to write over here to the side that open circle means that you're going to use parentheses. A closed circle means that you're going to use brackets, either right or left brackets. It depends on whether it's a starting or an ending point. Then for your range, note that range goes from low to high. So range, I'm going to have to cut this y-axis into the lowest part of the y-axis and the highest part. So sometimes this is harder for kids to see. But as I travel here, there's no graph until I hit here. Now there's a graph, part of the graph going along this part that has a y value here. So if I were you, I would highlight this cut in the y-axis, because at that value of y, which is at -2 here, we have the lowest y value. And then as we travel up the y-axis, we still have a graph until we hit here. Now there's no longer any graph going up. So this is the highest point of that graph. And again, if I were you, I would cut the y-axis at that highest point. So typically when I look at range, I'm going to look at the lowest point in the graph. It's here, and I'm going to cut to the y-axis. I'm going to look at the highest point and cut to the y-axis. And so my range, my y values are going to be from here to here. So this y value here is +2. So I'm going to mark that on here. So our graph went from -2 to +2, so we went here low to high, -2 to +2. Now the reason why there's brackets here is because over here this is closed. All the way up here this point is closed, so both of these should be closed. So then what I would like you to do is take this graph and do the same thing. I want you to find the domain and range using the same procedures or whatever works best for you. So pause the video, find your domain and range, and then restart the video to check your answer. All right, so I'm going to find domain first. Remember, domain is going to go this way. I want to cut the x-axis by the leftmost and the rightmost part of my graph. So this is the leftmost part of my graph, so I'm going to cut here. And this is the rightmost part of my graph, so I'm going to cut here. So I'm going to highlight my leftmost so I can split that x-axis and highlight my rightmost. I also want you to note this is a closed circle. This is an open circle. It doesn't matter what's going on in between here right now, as long as I don't note that there's any holes, and there are no other holes other than this one. So I'm going to go from 1, 2, 3, 4, 5. So this is a -5. All the way to 1, 2, 3. This is a +4. So my domain is going to go from -5 to +4. Then you have to determine, do I have open or closed circles? So I have a closed circle here, so I should have a bracket here. And then I have an open circle here, so I should have a parentheses here. Then for range, you're going to go from low to high. So my lowest part of the graph is right here. There's that relative minimum. And so you can use relative min and max to help you with your range. So this is the minimum part of my graph along here. And then my maximum, this is a relative max and this is a relative max. This is the highest relative max because I have two maxes, 2 points at which my graph is changing direction. So I want to choose the highest one. So that's my highest one. And so then my y values are -3 here. That's a -3. And then 1, 2, 3, 4, +4 here. So for my range, I'm going to go low is -3, high is +4. And then to determine whether I have brackets or parentheses, here at this low point, it's a closed circle. And here at this high point, it's a closed circle. So because they're both closed circles, we have brackets around both of them. Then I want you to highlight this right here. Remember to use a vertical line test to tell if it's a function or not. So if I'm going to use my vertical line test, I'm going to run a vertical line through this graph anywhere along it. So if I run the vertical line through here, this is a function because nowhere does my vertical line touch the graph more than once. Same thing over here, as I run my vertical line along this graph, it never touches it more than once. So therefore, this also is a function. So both of these are functions. I'm going to switch out my pointer. All right, then example 2, we're going to look at increasing and decreasing functions. Let me try to straighten this up. Okay, so I'm going to make this a little small at first so you can write a few things. So as we're looking at this particular function, it starts here on the left and goes down to this point. And then it goes horizontally. There's no up or down there till it gets to this point, and then it rises and goes up. So we are looking for decreasing, constants, and increasing parts of our graphs. And they're always in terms of x values. So when we look at increasing or decreasing functions, it is always in terms of x values. So this is a point, it has nothing to do with decreasing. These are separate. So they're always an open interval, and then you always look at the points which is where the transition occurs. In other words, the change of direction. So what does all this mean? So always defined in terms of x values. So I'm going to look at this graph and I'm going to determine where my increasing and decreasing parts of my graph are based upon what x is doing. So I want to see, as I go from left to right along the x-axis, what is the direction of the graph. So you're kind of looking at the y as you're moving from left to right on the x-axis. So as I move from left to right, my graph starts high and goes low, so this is a decreasing interval. And then as I move from here to here, my graph is neither rising nor falling. So this is called constant, it's remaining steady. And then as I go from here to here, my graph is rising, so that's considered an increasing interval. Notice that these right here are going to be our x values. So if I go ahead and do the same thing that we did with domain, and everywhere there's a transitional point, so here, 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 and here, and my transitional points, where does it change? So I start here, then I change direction here because I go constant. Then from here I change direction and go up, and I end there. So you want your start point and your end point, and you want any transitional point where we change directions, where we go to an increasing, to decreasing, or to a constant. So these x values are going to be important. So the x value of our start point is -2. Then we reach our next transitional x value point, and this is 0. Then our next x value transitional point, this is 2. And our next x value end point, this is 4. So I go from -2 to 0, and that's where you get -2 to 0. The graph is starting high and going low, so that's decreasing. Then from the x value of 0 to 2, I'm neither increasing or decreasing, so from 0 to 2, I remain constant. And then from 2 to 4, the graph is increasing. So I have that increasing, it's rising, so I have that increasing interval. So always in an open interval, you always are going to have parentheses here. And the reason for that is, at this point, right at that point, I don't know whether the graph is decreasing or remaining constant, because that's where the point of exchange is occurring. So we put open parentheses there at each of these transitional points. Then make sure you have all the points of transition, including that beginning and end. So here we go. For example 3, we are going to use, let me move this up, we are going to look at relative min and max, because relative min and max is going to help us find range. So they are actual points where the intervals go from increasing to decreasing. So that's why it's important to know whether your graph is increasing or decreasing, and then also vice versa. And you can use a calculator to find them. So it's going to be hard for me to show you my actual calculator and what I'm putting in there. So my assumption is that you know how to input these into the calculator. I'm going to show you what the graph looks like here. So when you're using your calculator to find my relative max or min, I'm going to put this part only into the y equals of my calculator. So step 1, if I were you, I'd write out your steps. So step 1, you're going to put your function into y equals. All right, and it's just the right side of that equation. Then for step 2, you're going to hit the graph button, and you should be in your standard viewing window unless you need to change it for some reason. For instance, to find the relative max or min, you want to see it in the window, so sometimes you might have to zoom in or out. And then step 3, once you graph it, you're going to go to the calc menu. To get to the calc menu, you're going to hit the second button and then the trace button, and that gets you to the calc menu. From the calc menu, you're going to either choose max or min, depending upon which one you're finding. And then you will follow the directions. It'll say left bound, right bound, guess. So just make sure you're to the left and right of that max or min, and then you can hit guess. So on this particular one, you really need to zoom in. Once you graph it, you're going to have to zoom in so you can see the curves and the relative max or min. So because I'm going to zoom in, I'm going to change my points here. This is going to be, let's see, this is going to be, I think I'll do, this is going to be my 1. So every fourth. This will be my -1. And this will be my +1. And this will be my -1. Okay, so I changed my scale because I'm zooming in. Then what I want you to do is you need to graph the following points. You need to graph your zeros. So in our case, once you graph these, your zeros end up being -1, 0. And these are places where the graph is crossing the x-axis. 0, 0. And I use my calculator to find these, and 1, 0. I also want you to find the max. So this one has a relative max. And in this case, we're going to round to 2 decimal places, so my relative max is 0.58 and 0.38. So you see all of my points are 1 or -1 and less. And then my relative minimum is going to be -0.58 and -0.38. Okay, so I'm going to graph these points. So let's see, -1, 0, and then 0, 0, and then 1, 0. And then my max is going to be to the right, about a half, and then up a little less than a half, like right here, give or take. It's just a sketch. Then to the left a half, and down a little bit less than a half, so like right about here. So then I'm going to connect those. So you should see this curve happening in your graph. So right here, this right here is your relative max, and this one right here is your relative min. And that's it. That's all there is to that. Use your calculator. It is your best friend right now. Let's move on. Okay, so here we have 4 different things we're looking at: even and odd functions, piecewise functions, and graphing step functions. So for our purposes in this class, this is not a standard, so we're not going to go ahead and graph step functions. So I'm going to go ahead and move this over, and we're going to look at graphing piecewise functions. Piecewise functions are actually kind of fun to graph because they're kind of like a puzzle. So what you need to know is that the domain of a piecewise function is restricted. Notice that both of these are at 1. When x, the value that you're inputting, is less than or equal to 1, you're going to use this function right here. But if your x value is greater than 1, you're going to use this function here. So we have to graph each of these functions together on the same graph, but using the restricted domain. So I like to put, since both of these are the same, I like to put a line, and you can highlight it. I like to highlight mine, where that's occurring. So on my graph at 1, this is the boundary, where to the left is one equation and to the right is another equation. So this is to the left of that boundary line, so I'm going to graph this function over here to the left, and this is to the right of this boundary line, so I'm going to graph this function over here to the right. So let's start with this. This is really y equals 2x plus 3. It's the graph of a straight line. So I'm just going to use my knowledge of y equals mx plus b. You could use xy tables. You're not going to be able to do this on your calculator though because of the restricted domain, but you can definitely do xy tables. This particular graph starts at positive 3 on the y-axis, and then its slope is a rise over run of 2 over 1 or negative 2 over negative 1. So if I rise 2 and run 1, I land on my borderline. So I have to determine, is this value, so if I plug in 1, and oftentimes I'll always plug in the border point. So if I plug 1 in here, 1 times 2 is 2, plus 3 is 5. And because it's equals to, I'm going to have a closed circle here, and sure enough, I landed here at 5 when I did my stair stepping for my slope. So because this is a less than or equal to 1, I'm going to close that circle. Then I'm just going to stair step my slope down 2 to left 1, down to left 1 all the way through. Then you should use a straight edge. I don't have the ability to use a straight edge on here, but you should use a straight edge. And so this graph is going to continue in this direction forever. The arrow goes here on the left side because my x can be less than 1 all the way to negative infinity. So it's going to just keep going down and to the left. On the right side, I'm going to use this function here to graph over here. Now this one starts on the y-axis at 4. But I'm supposed to be to the right, so my graph actually can't start here. Now again, I like to start, I typically will plug in my border points. I'm going to plug in 1 into here. So if I plug 1 into here, times a negative, I get negative 1 plus 4. So at 1, my y value is 3. So at 1, my y value is 3. I'm going to put an open circle because this is greater than it's not equal to. So this boundary point is not included in my solution. And then I'm going to move my graph in this direction. From this point, I can stair step the slope of down 1 to the right 1, down 1 to the right, down 1 to the right, or you can keep plugging in values. Okay, and I'm going to connect the dots on this one. All right, so you might want to write yourself a note. Plot boundary points first. That way you get a good knowledge of what goes along this line. Then for my domain, so as I walk the x-axis from left to right, my domain, this is continuing to go down and to the left forever. So to the left is forever, to the right is forever, and along this boundary point, yes, this is an open circle, but that closes that hole because here at a value of 1 for x, I will have a y value. It's not going to be here, it's going to be all the way up here. So I do not have a restricted domain. My domain goes from negative infinity all the way to positive infinity. Now for your range, it is restricted. Range we go from low to high. So all the way down here, notice that these are continuing down and to the left, down and to the right. So we have a graph down here infinitely. But as I rise, there's no more graph after this point. So this is the highest point of the graph. So my highest point is all the way up here at 5 on the y-axis. There is no low point to this graph because it keeps going and going. So for my range, my low point is negative infinity, and my high point is 5. The question is 5 included or not? So at that high point, that 5 is included because it's a closed circle. So I'm going to put brackets here. There's my range. All right, then let's talk about even and odd functions. So let me make this a little smaller so we can look at both of them at the same time. Now I'm making it crooked. All right. So you can do this a couple of ways. Best way that I can explain to you about determining whether a function is even or odd is this. If I were to take a function and replace every x in it with a negative x, and you get exactly the same function that you started with, no signs changed, nothing else changed, it will be called an even function. However, if I have an odd function and I replace every x in that function with a negative x, and I get the opposite of my original function, in other words, the opposite of my original function implies that every sign on every term of that function changes, then I have an odd function. Not every function is even or odd. You can have neither. So if when you plug in a negative x, and notice that both of these are plugging in a negative x, we're evaluating the function if we plug in a negative x. If you get exactly the same function, it's even. If every single term in the function changes to their opposite sign, then you have an odd. If only a few change their opposite sign and a few stay the same, then you have neither. So I would write in the following. We're going to replace x with negative x. I'm going to write that in blue, with negative x. So when we're, so replace x with negative x. I'm going to make that a capital. Results. Oh, I can't spell today. Results in identical function. In other words, you're going to get f of x. It didn't change. F of x didn't change. So let's look at this function right here. If I replace x with a negative x, what do I get? So if I have f of negative x, that equals something squared plus 1. So if I replace that x with a negative x, notice that I get negative x squared is x squared plus 1. Isn't this function identical to the function we started with? Nothing changed. Therefore, this is an even function. All right, so let's look at the other one. I'm going to move this over. And so for this one, just as I said, if you plug a negative in, all the signs change on the function. So I would write the following. Replacing x with negative x has the effect of multiplying the original function by negative 1. In other words, all signs change. So let's go ahead and find f of negative x. That's going to equal something cubed minus something. So negative x goes in here and in here. Note that when you cube negative x, you still get a negative x cubed. But here, a negative times a negative is a positive x. So notice our result. The x cubed changed to a negative x cubed, and the negative x changed to a positive x. Every sign here changed to its opposite sign here. Therefore, you have an odd function. If only this sign changed and this sign remained the same, then you would have neither. So it doesn't have to fall into the even or odd category. It could be neither. All right, now, symmetry. Let's look at the even function. So this is still part of our even functions. So I'm going to bring this down a little bit. So if you have an even function, you can prove that it is an even function by using your calculator and looking to see, is it symmetrical to the x-axis? So even functions are symmetrical to the, did I say x? Even functions are symmetrical to the y-axis. So highlight that. So we are going to prove by our calculator that it is symmetric to the y-axis, and I'm going to underline this. So I'm going to throw this into my calculator, or I don't even have to have a calculator. I could do a table of values. And I'm going to graph the original function. So I'm going to plug in the values of -2, -1, 0, 1, and 2. So if I plug these values into this function right here, I'm going to take -2 and square it. I get 4. 4 plus 1 is 5. Then I'm going to take -1 and square it. I get 1 plus 1 is 2. Then take 0 and square it. I get 0 plus 1 is 1. Then square 1, you get 1 squared is 1, plus 1 is 2. So we're starting to repeat values. Then put 2 in. 2 squared is 4, plus 1 is 5. So plot those points. And then connect your points. Now, if I had been looking at the graph only, I could determine that this graph is even because look at the y-axis. Does the y-axis cut this graph into perfect halves? This half is a mirror image to this half. So see, because of that symmetry, it's an even function. You can also look at your table of values. Notice that your x values are opposite. These are opposite signs to this, but your y values are the same. So even though these are the opposite signs to here, they still have identical y values. The 1s both have a y value of 2, and the 2s both have a y value of 5. So that is definitely something that I would put a circle around. So there's all kinds of ways you can determine if a function is even. So you can plug -x into the function, and if you get exactly the same function, it's even. You can graph the function, and if it's symmetrical to the y-axis, it's even. You can look at the table of values, and if your x values have opposite signs, but the y values have the same values as the opposite signed x, then it's an even function. Let's look at the odd function. So we can again prove by calculator. So I'm going to highlight prove by calculator that we have, or that we are, symmetric to the origin. So this time I'm going to underline origin. So I'm going to go ahead and graph this. And I use my calculator to help me graph this. So I put this into the y equals, and I went to my table feature of my calculator to help me out because this is a really tight graph and it expands numbers quite quickly. So for instance, at -2, my value for y was -6. So that pretty much, I can't go any further than an x value of -2 because I'm going to have a really big y value and I won't be able to graph it. So then I chose some points in between my integers. So I chose to do -1.5 because the more points I graphed, the better the shape of my graph. And the calculator was -1.9 for my y value. -1 is 0, so I'm going by halves. So then -0.5 gave me 0.4. I'm rounding to 1 decimal place. Then positive, oh, I forgot my 0. So then 0 would be my next point, gave me 0. And then positive 0.5 gives me a -0.4. And then 1 gave me 0. And then 1.5 gave me 1.9. And finally 2 gave me 6. Now I want to point out that my opposite, so notice my opposite values for x, they gave me opposite values for y. So these are not the same values. So my opposite values for x here gave me opposite values for y, opposite values for x, opposite values, well, okay, there is no opposite to 0, so we can't count that. And then opposite values for x here gave me opposite values for y. And again, of course, there's no opposites to 0. So both x and y values are opposite. So every time I had an opposite value in x, I had an opposite value in y. That is another way. So even before I graphed this, I could have told you, looking at my table of values, that this is an odd function. So I'm going to go ahead and graph those points. So -2, -6, -1.5, almost -2, -1, 0, so that's a 0 because it's on the x-axis, and then -0.5 up just a smidge, like almost halfway, and then 0, 0, so we're back down. So that looks like a relative max. And then positive 1/2, down almost a half, and then 1, 0, so there's another 0, and then 1.5, almost up to 2, and then 2, 6. So I'm going to connect those. All right, so symmetric to the origin. Here's what that means. So I'm going to put a highlight right there at the origin. I'm going to re-plot that point right there. Okay, what that means, if it's symmetric to the origin, they are the same distance from the origin. So notice that these 2 points are opposite of each other. I could draw a 180-degree line, and they're the same distance from the origin. Same thing with these 2 points, these 2 points, and these 2 points. I could connect all of them with a 180-degree line through the origin. So that's how you tell if it's symmetric to the origin. And that's all. So go ahead and apply. There's a lot of different things for you to learn and study. So you've got to study all of these different characteristics and features. So keep going back to your notes and reviewing and studying. Let me know if you have any questions.